MILP and models. In this session, we will have 3 papers. The first one is entitled Fast MILP Models for Division Property. The authors are Patrick Delbetz and Baptiste Lambing. Patrick will give the talk. Welcome.
Thank you for the introduction. So my talk is not really about division property, but much more about MILP modelization technique. But I still need to introduce a bit division property. So basically, you want to track some monomial in the ANF of a function f, but it's complicated. And so you have to decompose it into several layers for which you know valid transitions. And then you want to know whether there is a trail or not. And if there is a trail, you cannot conclude, but if there is no trail, then there is a distinguisher. And the accuracy of the technique depends on the decomposition you use for the function f. And if you want to increase the accuracy, you need to have less layers, so bigger layers. And all the recent works about this topic try to propose exact modelization of bigger layers. So for instance, for exact modelization of any linear layer, modelization of super S boxes, and so on. And if you look at this slide, you can see that in all recent works, they all abandoned MILP solvers for SMT solvers, SAT solvers, or ad hoc algorithm. And what we wondered when we started this work was if it's possible to have the same efficiency with MILP solver. And so we try to improve MILP modelization for division property. So an MILP model is a set of linear inequalities with some variables that are integers and some that are continuous. And in practice, with cryptographic problems, all variables are most often binary ones. And of course, MILP solvers are not magical tools. And for some models, it might take a very long time to get a solution or to solve it. And so sometimes we need to improve the models we write. And there is many ways to do that. So for instance, we can reduce the number of variables, reduce the number of inequalities, or we can change completely the strategy and, for instance, add a dedicated branching strategy or solve another problem, which is much easier to solve. And so I will show you how we applied those techniques to MILP modelization of division property. So first, we used an important property of the two-subset bit-based division property, which is that if we have a valid transition UV, then there are a lot of other transitions U prime, V prime, that can be safely added or removed from the model, meaning that adding them or removing them will not affect the validity of the model. And originally, this property was used to remove all non-minimal transition, but we found that it's much better to add all of them into the model because it will simplify a lot the constraint. So for instance, with two simple operations, the binary AND and the modular addition, so they both can be written with fewer inequalities. But actually, if you look at the inequalities in red, they are completely useless for the model, okay, to conclude on the existence of a solution or the non-existence of a solution. So for instance, if you look at the AND operation, the red inequality only ensures that if you have all zeros, you will get a 0 at the end. But in practice, we really don't care if b is equals to 1. Okay. And for, for the modular addition, it's a bit more complicated. But if you have, if the first inequality is satisfied, then similarly, the second inequality only removes a non-minimal transition. Okay, so we can remove it. It is also very useful for the Quinn-McCluskey algorithm. So it's very common when you want to modelize some cryptographic technique into a MILP problem to have some tuples of points for which there are impossible values. And you can use a simple technique to discard each of these values one by one. Okay? And then you can use the Quinn-McCluskey algorithm to reduce the number of inequalities. So how it works, you just search for vector spaces of impossible values. So first there is a saturation phase in which you will merge impossible values together and find some vector spaces for which all values are impossible. Okay, and if you apply that to this example, you will reduce the number of inequalities from 6 to 3. And actually, so this is an NP-complete problem, and the complexity is exponential in both time and memory. So this is so you are very limited on the size, on the number of variables you can handle with this technique. But if you use the property I mentioned before, actually you can completely remove the saturation step of the Quinn-McCluskey algorithm because it's combined very nicely with it, and you directly obtain all the vector spaces of impossible values. And so you just need to find a minimal cover. And so it's much easier. It's easier. And finally, when you have reduced the system of equations, then you can combine some of those equations, inequalities, by looking at inequalities that have all the terms in common but one. Okay, so here we can solve it exactly, but in practice, a greedy algorithm is efficient enough to find a good solution. Okay. So we improved this Quinn-McCluskey algorithm to compute possible valid transition through any Boolean function, but actually it works for S boxes, and this is the use case. We also proposed piecewise modelization for S boxes. So basically, the idea is to have a modelization like for word-based division property. So we just, sorry, it moves. We just modelize the transition of weight. And it works because in practice, what you want to do is to ensure that if the weight of the output is 0, then the weight of the input will be 0. And if the weight of the input is n, then the weight of the output will be n as well. And for most of the S boxes used in cryptography, that's all the only property you want to modelize. And okay. And for the linear layer, we also propose to use only the weight equality, which is exactly what it is used if you do a word-based division property. The problem is, so we introduced some new modelizations, but some of them are exact, so all valid transitions are represented, but some of them are lossy. It means that they allow some transitions that are invalid and which can affect the validity of the model. Okay. And if you have that, we need a way to remove those false positive trails. And we do that by using a callback. So it means it's a functionality of Gurobi and of some MILP solver. So when we find a solution, we check it. And if it's not correct, we will add an extra constraint to remove it. And so we need extra constraints, and we need to be able to generate those extra constraints. So for S-boxes, it's not a problem. We can use the QM algorithm or the convex hull algorithm to generate the exact modelization and add the constraints we need. But for linear layers, it's much more complicated because the only exact modelization is from Zhang and Reimann. So it's a ZR method, but it's exponential in the size of the matrix. Okay, and we don't want to compute all those inequalities because we can have a lot of them. And what we show is a paper is that we can compute the ZR method, but only locally. Okay, so you don't have to compute exactly all inequalities for the ZR method, but only locally. When you find a solution, you can check if it is correct or not, and if it is not, you can just compute one inequalities that you would obtain with the ZR method, but and that will discard the solution you just found. Okay, so it's just about discarding the minor you just extracted. And if you look at the time complexity, at the running times, you can see that we are much more faster than all previous works, and all our running times are obtained on a laptop. So it's a not very powerful laptop. While, for instance, the results from DF20, that's me and Pierre-Alain, they were obtained by using a 128 core server. So, for instance, for height, it's really, really faster for all of them. So basically, here in conclusion, we improved the modelization, the models enough so that MILP lead to the best running time. One word on the modelization we used. So at the beginning of this work, we believed that the best modelization will be to use a word-based division property modelization and only add callbacks to remove some pathologic cases. But in practice, it's very, very slow. And it's much better for S-boxes to use the exact modelization and for the linear layer to use the copy XOR modelization, because the copy XOR modelization ensures you that when you extract a minor, each row and each column will contain at least one 1. So it's not trivially non-invertible. And what are interesting here are those 3 columns, because it's the number of inequalities we added during the callbacks. Okay, so from exact modelization. And as you can see, not a lot. So for instance, for linear layer, it's like 100. So not exponential in the size of the matrix. And more interestingly, for the super S box, it's also very few. Okay, so for instance, for height, we didn't add any constraints coming from the modelization of the super S box. And actually, when we proposed to modelize the super S box, we thought it improved the accuracy of division property, but those results show it is not. Okay. It does not improve actually the accuracy. It only improves it only allows you to search for extended distinguisher, so to find how which linear layer add in front and at the end of your distinguisher. But it seems that's all. And one word about the weight equality. So why this modelization does not work in practice? The question is, what is the probability for a minor of an invertible matrix to be invertible? And you know that if you take a random binary matrix, it will be invertible with a good probability. But the matrices we used in cryptography are not random and are very sparse. And so actually, when you look at the minor for the AES matrix, the AES mixed column matrix, you can see that the probability that a minor is invertible is very, very low. Okay, and so I think I have no proof, but I think this is why this modelization is not very efficient. Okay, you will have a lot of non-invertible minor, and so you will have to add a lot of inequalities if you use it. Okay, so in these papers, we propose new modelization techniques, and I'm sure they can be used to improve other modelization for other cryptanalysis techniques. And we show that it is better to not add all the, to not have exact models, actually. I think the model should contain only the important inequalities, and the other one should be put in a callback, and you only add them to the model if they are needed. The code is available on GitHub. You can look at it. Okay. Thank you for your attention.
Thanks. Any questions from copy or chat? Any questions here?
Oh, there is a question from Beijing. Thanks for your presentation. I have a question. From the page 19, I found that you used different strategies for different ciphers. But for new ciphers, how do we find the suitable modding strategies? For example, which one should we choose from PWL plus WE or QM plus WE or others?
Yeah, okay. So I think for S-boxes, you should always start by using an exact modelization, because typically S-boxes are are small enough. So it's better to directly use the exact modelization. For the linear layer, I think you can start by using the copy XOR modelization. It will add extra constraint and extra variables to your model, but it's the fastest one. Otherwise, I have no real recommendation. I think if you can use the copy XOR modelization, you should use it. Otherwise, you should use weight equality if you have a very big matrix. And for Skinny, we used the QM modelization for the linear layer, but that's a particular case. It's because the matrix used in Skinny is a binary one. And so actually it's, again, a very, it can be seen as a very small S-box. And so it's better to directly add the constraints. That's all. I think what you want to do is not to add too many constraints.
Thank you. I got it.
Any other questions? Okay, let's thank the speaker again.
There is another question. Sorry.
Thanks for your presentation, and I have a question. As we all know, there are many different types of cryptanalysis, like the cube attack or the differential cryptanalysis. And so my question is, in which type of the cryptanalysis do you think this MLP first MLP model can apply to them?
I don't know, because so the modelizations we present in the paper are dedicated to the two subset bit-based division property. But I think the idea to not solve an exact model, but only a lossy one, and to add some extra constraints if needed, can be applied to any other cryptanalysis technique.
Okay, thank you.
Okay, let's thank the speaker again. Let's move to the next paper. It is entitled Super Bowl, a new approach for MILP modeling of Boolean functions. The authors are Yao Sun and Ting Li. Ting will give the talk. Welcome.
Thank you for introduction. The title of this report is Super Bowl, a new approach for MILP modelings of Boolean functions. And this is joint work with Yao Sun. This is outline of this report. First, I will discuss motivations and contributions, and then I will introduce our approach to generate inequalities of Boolean functions and to construct MILP models. At last, we will show some experimental results. MILP is one of the most powerful tools in symmetric cryptanalysis. With this technique, we can convert some hard problems into MILP models, and these models can be solved by MILP solvers automatically. In fact, MILP was first used to attack BVM in 2009, and since then, it has been widely used in cryptanalysis, including differential attacks, cube attacks, and so on. Generally, to describe the behavior of entire crypto system, we need to deduce Boolean functions from components such as differential distribution table, linear layers, and so on. The input values of Boolean functions are binary vectors, which can be seen as points here. And the support of Boolean functions are the input values that give non-zero output of functions. And the goal of modeling a Boolean function is to find a set of inequality that their common solutions are the support of the functions. Here we can the black points can be regarded as the support, and the red lines can be seen as the inequalities. However, there are multiple ways to construct MILP models, and these models may have different computational time, even if they have the same solutions. So the problem is, which type of MILP model could achieve the best efficiency? To address this problem, there are 3 steps. First, we need to generate various inequalities for Boolean functions as candidate. Once we got enough candidate, we can construct various types of MILP models by selecting inequalities from the candidates. And in this step, we need to consider relevant factors. And at last, we compare the efficiency of MILP models we generated. And this can be done by running them on test instance. So according to this, we make 3 contributions in this paper. First, we proposed a novel approach called the Super Bowl approach to generate various inequalities. And then we improved the Sasaki-to-do method to construct the MILP model by considering both sides and strings. The definition of strings will be given later. At last, we found a type of model that has better efficiency in most of our experiments. And this is the previous works related to generating inequalities of Boolean functions. In 2014, Sun et al. Proposed to compute H representation of the convex cone by using Sage software. But this method can't be used to generate inequalities for 8-bit S boxes. They also proposed the logical condition modeling method. But each inequality generated only removes a single point, resulting in a very large MILP model. Another approach is to compute product of some representation of Boolean functions by using Logic Friday software. However, the coefficients of this coefficients of the inequalities generated by this method are either 0 or 1. And in FSC 2020, the logical condition modeling method was improved to generate inequalities that removes the points in standard ball or distorted ball. So all the previous works only generate some special kinds of inequalities, which may not be sufficient. So we proposed a method to generate various inequalities by using the method of undetermined coefficient. In this report, we use some examples to explain our approach. Example 1 gives a set of points i's. We want to compute a polynomial f such that f is non-negative on all the points in i's. And the point in i's are the 4-bit vectors. For example, here, 100 means the point y00 means that x0 is 1 and other bits are 0. So to ensure that f is non-negative on all the points in S, we can regard the coefficients AI and B as unknowns, and we formulate the following constraints here. The constraints ensure that f is non-negative on all the points in S. The coefficients can be determined by solving the system of inequalities. And once we got coefficient, we can generate a polynomial f. And this is example 2. It is similar to example 1, but with an additional requirement. In this example, we want to compute a polynomial f that f is non-negative on the points of i's, and the set of points where f is negative is as large as possible. So we list the possible constraints here, but we can't add them into the system directly because it is uncertain which constraints could hold at the same time. If we add them into the system directly, it may lead to infeasible solutions. So to solve this problem, we use a binary variable yv for each point that not in S. And we have the constraints 3. Thus, if yv is 1, we have fv must be must be negative. Otherwise, fv is less than gamma. Here, gamma is a very large positive constant. So there is no constraints on fv in this case, actually. And the number of points where f is negative is equivalent to the sum of yv for v not in S. To make it as large as possible, we can add it into the objective function. And here is the MILP model we formulated to compute the polynomial f. And the number of constraints is 2 to the power n. As n increases, the number of constraints increases exponentially, and the system becomes harder to solve. So to make the problems easier to solve, we use the divide and conquer strategy. We can divide the coefficients into many patterns by fixing the signs of the coefficients, and then the problem can be simplified and the constraints are reduced. Here, for example, we can divide the coefficients into 4 patterns by fixing the signs of A2 and A3. Thus, in pattern 1, A2 and A3 are both non-negative. Here we show how to generate a polynomial in pattern 1. As shown in this slide, some constraints become useless. For example, here, we already have A0 plus B is non-negative. So A0 plus A2 plus B must be non-negative, and these constraints become useless, so we can eliminate it. Thus, we only need to consider the points in B, which is a subset of S when we formulate this type of constraints. And next, if we for the points that not in S, we can eliminate some constraints as well. The last 3 constraints can be eliminated because they cannot hold, since the blue parts here, because these blue parts are constrained to be non-negative, so they cannot hold. And we only need to consider the points in R in this type of constraints. Thus, in this way, the number of constraints can be reduced from 16 to 11 in pattern 1. And what's more, the MILP models in different patterns can be solved parallel, which will speed up the computation. And for other patterns, we can transform, if we want to compute a polynomial in other patterns, we can transform it into compute a polynomial in pattern 1. And our approach could generate other types of inequalities. Here are 2 examples. The first is to compute a polynomial such that the set of point where f is 0 is as large as possible. And the second is compute the spaced polynomial. Here, the sparse polynomial means the coefficient of the polynomial, most coefficients of the polynomial are 0. Since our first goal is to generate various inequalities as candidates, so we want to test the diversity of our candidates. And we constructed the minimal model by selecting inequalities from the candidate we generate, because the size of minimal model could reflect the diversity of the candidates. And here are the comparisons of the minimal size of the models generated by different approaches. The Boolean functions in the left figure are deduced from 4-bit S boxes, and in the right figure, they are deduced from larger S boxes. From the results, we can see that our model always has the smallest size, and it reflects that the candidates generated by our approach has a good diversity. Since we have got enough candidates, we can construct an MILP model. Sasaki to-do method is a common method to construct MILP models. This method assigns binary variables to each inequality, and the value of 1 indicates that the equality is selected. And in this table, the element in this table, the value 1 in the column I and row J means that the point J can be removed by the equality I. So to ensure that each point that not in S can be removed by at least 1 inequality, we add the constraints in the right. And the number of selected inequalities is equivalent to the sum of the i's, so added into the objective functions. Thus, Sasaki to-do answer generated the model with the minimal size, but it does not always lead to the best efficiency. Some researchers pointed out that an efficient model should balance size and strength. Here, the size refers to the number of variables and constraints, and strength refers to the search place that the solvers need to explore in order to find solutions. For example, in this figure, the model P prime has a smaller strength than model P. So the strength of model P prime is larger than model P. And the model constructed by convex hull always has the largest strength. However, the strength is hard to calculate, so we define approximate strength to measuring the strength of a model. We notice that in convex hull method, the points often lies on many hyperplanes of the inequalities. So we use this feature to design the approximate strength. And the blue part of this definition is the number of hyperplanes that the point V lies on. And the approximate strength is the minimum of the number for the points V in B. Here, B is the set of outermost point in feasible region. And here are two figures to illustrate the approximate experience. In the left figure, it is 1, and in the right figure, it is 0 because there is a pointless on no hyperplanes. And we also define cover rate to compare the strength of the models when the approximate strength is 0. And the cover rate is a ratio between two parts. The first part is the number of the points that lies on hyperplanes, and the second part is the total number of the outermost points in feasible region. And with these two definitions, we can improve the Sasa key to do method to compute the model that balance size and strength. We want to compute the model with a minimal size among the models with an approximate strength being at least S. So here we use example to illustrate it. And in this table, we use 0 bar to indicate that the point Vj lays on the hyperplanes of the inequality I, and to make sure that each point in S, the number of hyperplanes that the point in S lays on is at least S. We add the constraints in right. If there are points, if there are points that lays on the hyperplanes, that is to say, approximate strength is 0. We want to compute a model with the minimal size, and the cover rate of this model is maximal in this size. So we use the binary variable Ci to indicate that whether the point I lays on some hyperplanes or not. And the cover rate is determined by the sum of i's over added into the objective function. So in this way, we can formulate the MILP models to construct the balanced model. And at last, we use our approach to model the Boolean functions deduced from the S boxes of Lilliput and Skinny 128, which is an 8-bit S boxes. And we generate 4 types of balanced models. We also compare their efficiency with the other models that generated by the previous methods. And this table shows the size, approximate strength, cover rate of each model. And to test their efficiency, we designed 2 traditional search tasks. Task 1 is the verification of differential pairs, and the second task is finding the minimum number of active S boxes. And from the results, we can see that the balanced 0 CR max, which has the max cover rate, has a better efficiency in most of our experience, although there's no model has the best efficiency in all cases. And this is our experimental results. And that's all. Thank you.
Thanks. Any questions from Kobe or chat? Any questions from Beijing?
There is a question in Beijing. I noticed that Sorbal can model 8-bit SBOS. How long will it cost if there are many patterns to calculate?
Because the different the MILP models in different patterns can be solved parallel. So if the thread is enough, it won't take too many times. For 8-bit hours, for example, Skinny 128, it maybe take several hours to solve all the problem, all the polynomials.
How about AES SBOS?
In fact, AES box is more easier to solve because the number of points in B and R is smaller than a skinny, but the solving time of each pattern is shorter. But if you want to construct the minimal size of model, it will take a long time because the candidates is too much. The inequalities in the candidates is too much.
The improved ST algorithm will cost a lot of time.
What? Pardon? Which one?
Select or equality set. Is that will cost a lot of time?
Sorry, please repeat again.
If we have get a lot of candidate equalities, we should select some equality set by improved ST algorithm.
It's out of time, so you can discuss it in private.
Okay. Thank you.
Let's-
Thanks you for your answer.
So thanks the speaker again. Let's move to the last paper. It is entitled SOC, Modeling for Large S boxes Oriented to Differential Probabilities and Linear Correlations. The authors are Lin Sun and Meiqin Wang. Lin will give the talk. Welcome.
So thanks for the introduction. Hello, everyone. The name of the presentation is SOK, Modeling for Large S boxes Oriented to Differential Probabilities and Linear Correlations. It's a joint work with Meiqin Wang. We start with motivation and contributions. After more than a decade of development, automatic methods for differential and linear characteristic search are well established. The methods based on MLP and SET or SMT are two of the most popular. However, both for these methods, searching for actual differential and linear characteristics for large S boxes is not conclusive. So in this work, we intend to solve, or we say partially solve this problem. That is how to efficiently create set models for large S boxes. So based on this motivation, 3 strategies are proposed. And with these new set models, we have some new findings about some primitives, and we will introduce this later. Now we briefly review MLP modeling progress for large S boxes. If we want to create a set model for an S box, each bit of the inner state should be allocated with a binary variable. And the simplest model for an S box is to describe its star DDT. It is a reduced form of DDT, and all non-zero entries in the DDT are replaced by 1 in the star DDT. So with the information in the star DDT, we can create 2 sets. The first one contains all vectors representing possible propagations, and the second one contains vectors representing impossible propagations. Sun et al. Proposed the first bit-oriented model for S boxes. So if we want to create a model for the star DDT, we can, using linear inequalities, to represent all possible propagations or remove all impossible propagations. These two ideas corresponding to two approaches. In the first approach, we treat all possible propagations as a set, and its convex hull is defined as the smallest convex set containing 8. The convex hull can be represented as a common solution of a system of linear inequality, and we call it the H representation of the convex hull. So, given a convex hull, its H representation can be obtained by applying some functions in this class of sigmas. The second approach is called logical condition modeling. It creates inequalities to remove impossible propagations one by one. For example, this is an impossible propagation and we want to remove it. Then we create these inequalities and it becomes invalid only when the values of x and y takes these values. So apparently, applying this method directly will result in an excessive amount of linear inequalities. So to settle this problem, Sun et al. Found that certain S boxes contain conditional differential property. It allows us to remove multiple impossible propagations with a single inequality. For example, here we have an impossible propagation, impossible differential pattern, which means if the input difference of the S box equals 9, the last bit of the output difference should not equal 1. So it contains 8 impossible propagations, and with this single inequality, we can remove all these 8 impossible propagations. The problem is that conditional differential properties that do not present in all S boxes. Moreover, this method mostly applied to lightweight ciphers. At FSC 2018, novel modeling for large S boxes was proposed. Instead of using a manual way to combine inequalities, the authors first create a 2n-bit Boolean function f, and f equals 1 if and only if the input vector is a possible propagation. Then f can be represented in this form. It is called the canonical POS form of f. And note that the 1-bit XOR here can be represented as this form. So up to this point, this method is almost the same as the previous one. The new idea is that the authors found that lowering the number of inequalities is akin to simplifying the POS form of f, and this question is a well-studied one. And the Quinn-McCluskey algorithm can be used to determine the minimum POS. However, this algorithm also becomes infeasible even for moderately large functions. So an illustration in the paper is that the author showed that reducing a 16-bit function corresponding to the star DDT of AES is already infeasible. So in this case, the heuristic algorithm Espresso was suggested so that we can maintain the number of inequalities as small as possible. Although many researchers pointed out that minimizing the number of inequalities does not always reduce the runtime of the MLP optimizer, many subsequent studies continue to seek a breakthrough on the number of inequalities. We list some of them here, also including the work in the last presentation. In this work, improved MLP models for the S box of AES and the Skinny 128 was proposed, but they were not employed to analyze the differential characteristics of these ciphers. But we have to admit that minimizing the number of inequality is of theoretical importance in its own right. Now we briefly review set or SMT modeling progress for S boxes. The use of set for the search of distinguisher in cryptography was first introduced by Mohan and Preneel at 2013. This work, the following works, mostly focus on the search oriented to AIX ciphers. The S-box model proposed by Ankler and Colby is very similar to the logical condition modeling in MLP. It also tries to create Boolean equations to remove impossible propagations one by one. Also, for this impossible propagation, we can create this Boolean function. Obviously, it's a clause, and this clause is invalid only when the values of x and y takes these values. So also, this method, applying this method, also endures the problem of having too many clauses. So later, Sun et al. Proposed a model with simplification and is also inspired by the method in MLP approach. We first review the modeling oriented to active S boxes. So in addition of the binary variables corresponding, in addition to the binary variables corresponding to the input and output differences, there should be an auxiliary Boolean variable omega to indicate the state of the S box. And the value of omega equals 0 if the S box is inactive, and it equals 1 if the S box is active. So according to this criteria, the possible values of this vector should fall into this set. So if we use the direct methods that remove impossible propagations one by one, the number of clauses in the set model will be extremely high if the size of this set is enormous. So similarly to the work at FSE 2018, we create a Boolean function with the support being this set. And after simplify these functions, we can obtain, also use Klein-McCluskey and express algorithm, we can obtain a simplified set model. When it comes to modeling oriented to differential probabilities and linear correlations, additional auxiliary variables are required to encode probability and correlation information. And in this presentation, we always focus on the weight of possible propagation. And note that this value can take on non-integral values, so we should introduce variables for both the integral and decimal portions. Now we consider a 4-bit S box, and its DDT contains these values. And then the set of probabilities for all feasible differential propagation looks like this. So to encode this probability, we should introduce 3 variables to represent the integral portion and 1 variable with 0 to represent the decimal portion. Then an optional set of possible values for this vector is created just like this. And note that the vector in this set confirms this equation, and it allows us to create objective functions considering the probability of differential characteristic. Also, this set can be regarded as a support of a Boolean function, and the set model for differential probabilities can be derived by simplifying the canonical POS form. We should note here that all the set models cannot be used for large S boxes, since the creation of the set model includes the simplification of a large scale function. Now we introduce our fast set models for large S boxes. In total, we proposed 3 models, and the first model centered on Espresso itself. We found that Espresso provides multiple options and commands for minimization, and these options and commands create a trade-off between the simplification level and execution time. Here, we list several options that may reduce the runtime, and it can be noticed that these options ignore or skip several operations in Espresso so that we can achieve potential acceleration. These options are used to conduct the simplification of this function. It is a 26-bit Boolean function and occurs in the description of DDT for Skinny 128. The simplification is only accomplished with the last option, onset option. There are 820 clauses in the output, and the total execution time is about 1 hour. Also, although the number of inequalities is not guaranteed to be the minimum, but the execution time is in an acceptable range. The second model is called two-step encoding method. We found that the complexity of simplification increases exponentially with the number of input variables. So the main idea is dividing the encoding phase for an n-bit text box into 2 steps. So to realize this goal, in addition to the auxiliary variable u and v for the weight, we claim a set of training variables z. To have a better understanding, we take the 8-bit text box of Skinny as an illustration. This set contains probabilities of all possible propagations, and in the previous method, we should simplify a 26-bit Boolean function. And with the new method, we introduce 4 training variables. And in the first step, we create a connection between the probability and the value of training variables. And in the second first step, we should simplify a 20-bit Boolean function. And in the second step, we create a connection between the value of the training variable and the value of u and v. So in step 2, we should simplify a 14-bit Boolean function. So with these 2 steps, we also realize the goal to create a connection between the probability and the value of u and v. But the simplification of a large-scale function is converted into the simplification of 2 relatively small-scale functions, so that we can create the set model more efficient. Different options are applied to the 2 functions for Skinny. And from the table, we can notice that if the onset option is applied, the 2-step encoding approach is still highly efficient when the total time is comprised of the simplifications of the 2 functions. The total runtime is about 98 seconds, and it is much less than the previous one without using the 2-step encoding method. Also, the amount of clauses for 2-step method is 787. It is also less than the previous one without the new method. The third model is based on the observation in the test. We found that the simplification of a large-scale function is not difficult if the number of clauses in the function is not excessively huge. So before we introduce our method, we first review the definition of partition. So given a set X, its partition is defined as a family of sets, and this set should satisfy three conditions. The first one is the family does not contain the empty set. Secondly, the union of the sets in the family equals to X. Thirdly, the intersection of any two different sets in the family is empty set. So with this definition, we go back to the canonical POS form of F. In the previous introduction, we already know that F can be represented as the conjunction of multiple clauses. And now if for this set, we can find a partition looks like this, then the conjunction can be decomposed. Further, F can be represented as a conjunction of L subfunctions, and each subfunctions will have fewer clauses than the original F. Now, if a simplification F tiered I can be found for each Fi, then the conjunction of this simplified function yields a simplified form of F. So the question for now is how to construct this partition. So we go over the Klein-McCluskey technique and find that grouping clauses by the Hamming weight may facilitate the simplification. So we hypothesize that the simplification could be made simpler if the clauses in a given set shares as many bit values as possible. So to create a general method of partition, we start with the partition of the set F2N. Here, we use this symbol to denote a subset of this set, and all vectors in this set should satisfy the first bit value equals to this value. With the following figure, we may have a better understanding. So in the first set, all vectors in the first set should satisfy the first S bit value equals 0, and the remaining N minus S bit can take any value.
Can you be a bit faster, because it seems you exceed too much time?
Okay. So in this way, we create in total 2 to the S sets, and the family of this set constitute a nature partition of F2N. And when the partition is restricted on the set we are interested in, it turns into a partition of this set. So now that we have a partition, it already permits the decomposition of the function into 2 to the S subfunctions. And if we apply expressor one time and take a conjunction of the simplified function, we find that the number of clauses in the simplified form is typically quite high. So we come up with iterative simplification method. And after apply expressor one time, we combine the simplified function in pairs and reapply expressor once again. And this simplify and combine procedure is repeated until we find the final output. So it can be imagined that the level of simplification of the final output and the runtime are affected by the number of components in the initial partition. We did several tests in our paper, and we only show one of them here. It can be noticed that for some values of S, the runtime for expressor is less than the one without partition. Also, the number of clauses are slightly reduced. Now we have several new findings with the new set model. The first one is that the previous work attempted to get tight upper bounds for the probability with MILP model, and the task was completed up to 13 rounds, but for 14 rounds, they merely demonstrate that no characteristic had a probability greater than 2 to the minus 128. And in this paper, we used our new model to analyze skinny 128 and found that The upper bound on probability for 14 rounds is 2 to the minus 138. Therefore, finishing the remaining task of the previous work. The second application is to analyze AES-based constructions. We analyze the 7 constructions, and for 2 constructions, we improve the lower bound for the number of active S boxes, therefore provide more precise analysis results for these 2 constructions. And for the remaining 5 constructions, we confirm the previous work. So a brief conclusion. In this work, we propose 3 strategies to create set model for large S boxes. And with these models, we have several new findings. Note that this part is not shown in the presentation, and details can be found in the paper. So that's all for the presentation. Thank you for your attention.
Thanks. One quick question. If there is no question, let's thank the Lin again and all the speakers. Thank you.
Hello, everyone. So we will take a bus to Beihai Park for the banquet. You can bring back your belongings to the hotel room and then to take the bus at the door of the hotel.